Hi guys, welcome back to series on working of lamps. So let's continue our discussion of working of lamps. Now I will go through the templating process of our problem in hands, which is viscosity, very quickly. My focus will be to define how are four sections broken down here and what are the commands coming under these parts, and more precisely we will see syntax of these commands. And in coming video I will write this code in notepad plus plus, and we will use there how to write a problem in hands into lamp syntax. One of the simplest command is the variable command. Just like other programming language, it is used to define a variable that can be used anywhere in the script. Its style is as follows. It starts with a variable word followed by at least one white space, and then comes the variable's name, which is X in the first line of code here. Excuse me. Then we define style of variable command. As there are many styles, variable of style equal assign a value or store a formula which when evaluated produces a single numeric value. So variable X stores value of X. We can also define type of units in this section, which in present case is Leonard John. In the next section of system definition, we first define the parameter of the simulation box, and we label these commands as setup simulation box command as discussed earlier. So I like to discuss 5 commands here. First one is the dimension command. It set the dimension of simulation, and 2 means 2D simulation, while 3 means 3D simulations. Syntax is simple as it is written here. Next is the atom style command. Its syntax is command name, which is the atom style, then style of atom style command, and finally its arguments. Once a style is assigned, it cannot be changed. So use a style general enough to incorporate all attributes. For instance, with style bond, angular terms cannot be used or added later to the model. And it is okay to use a style more general than needed, though it may be slightly inefficient. All styles store coordinates, velocities, atom IDs and types, but the choice of style affects what quantities are stored by each atom. What quantities are communicated between processors to enable force to be computed, and what quantities are listed in the data file read. And next is the latest command. The syntax is as follows. Latest style scale keyword values. Style can be a crystal system of choice, for example square lattice here. The argument of the lattice command can be used to define a wide variety of crystallographic lattices such as BCC, FCC and hexagonal. Scale means scale factor between the lattice and simulation box. For example, you can define your lattice constant here. 0 or more keyword value pairs may be appended. For instance, you can set your origin or orient lattice directions, or define lattice spacing in X, Y or Z dimension, or set your primitive cell vectors A1, A2 or bases. Next is the region command. Its syntax is region, ID, style, arguments, keyword and its related arguments. ID is a user assigned name for the region, which is simbox here. Style can be delete or block, cone, cylinder, or prism, etc. Style block defines bounds of block in all dimensions with argument as starting and ending values in each dimension, which is x and y in 2D, while also includes z for 3D simulation. And 0 or more keyword values can be appended. Fifth command here is create box command. Its syntax is create box, n, region, id, keyword and value. N means the number of atom type to use in this simulation. In present case it is 3, means there are 3 types of atoms. Region ID means the already defined region, ID of the region to use as a simulation domain, which is simbox here, which is the region we have defined earlier in the previous command. Next, the categories of command that comes under system definition section is setup atom commands. First of them is create atom command. Its syntax is as follow: create atom, type, style, arguments, keyword and their values. Type defines the number of atom types, and for the box style, the create atom command fills the entire simulation box with particles on the lattice points, and one or more keyword pair can be appended, and of course nothing is required here. For the particular case, no keyword are required here. Syntax of mass command is mass I value, where I is atom type and value is mass value of that type. Next is the neighbor modify command. It sets parameters that affect the building and use of pairwise neighbor list. Its syntax is simple: neighbor modify keyword values. The delay keyword means never build new list until at least n steps after the previous build. After the delay has passed, every setting means build list every m steps, means every one step. So let's move on to the next section, and here the next section is simulation setting. Region command is defined here once again. Now we are using it to define different regions in simulation box, so same command can work in two categories. For setting categories, we are defining some region in the box. First is the lower region of the style block with the most bound values as inf. What does this inf mean? INF. It means assigning a very large number to a particular bound so that even if the box size changes, the bounds will still be the size of the simulation box in that bound, the one with the bound value of inf. For a lower block, X direction starts from where the simulation box starts and ends where the simulation box ends. For Y direction, lower Y starts from where the simulation box starts but ends at the 0 point here. And lower and upper bound for Z direction are inf. We are not doing 3D simulation, but still we need to certify LAMMPS by providing Z direction. For upper block, X direction maps the simulation box size while Y starts from 20 to the size of simulation box. Next we group atoms. As we have defined the region lower and upper here, we should also define the atoms confined into these regions as upper and lower group of atoms for the upper and lower region respectively. Syntax of group command is simple. It's group id, style and arguments. id is equal to the user assigned name of the group. Various styles are possible, and region style puts all atom in the region volume into the group. If we see next two group commands, then here we see style equal the union. The union style takes a list of one or more existing group names as the arguments. All atoms that belong to any of the listed group are added to the specified group. So the upper and lower group are named here wall together. This subtract style takes a list of two or more existing group names as arguments. All atoms that belong to the first group but not to the other groups are added to the specified group. We also have a set command. Its syntax is set, style, id, keyword and values. Set command set one or more properties of one or more atoms. Since atom properties are initially assigned by the read data, read restart or create atom command, this command changes the assignments. This can be useful for overriding the default values assigned by the create atom command. Here we are setting the type of atoms for the upper and lower region. We're setting the upper group of atoms to type 2 and the upper to the type 3 and the lower to the type 2. Finally, we have velocity command. This is one of the most important command. We have its syntax as follows: velocity, group id, style, arguments, keyword and values. Group id equals the id of a group of atoms whose velocity will be changed or depending on the style created or changed. And there are many styles available. For the create style, we need to provide temperature and a seed number. Create style generates an assembly of velocities using a random number generator with a specified seed at the specified temperature. The set style set the velocity of all atoms in the group to the specified value. Here it set the x component of velocity of upper group equal to 2.7 LJ unit. S rate, we have already defined the S rate in the previous slide. In the system initialization setting, let me show you here. Here we have defined it 2.7 and it's in LJ unit. The unit keyword is used by the set style. If units equal box, the velocity and coordinates specified in the velocity command are in the standard unit described by the unit command. If units equal lattice, velocities are in units of lattice spacing per unit time, and if coordinates are in the lattice spacing. But we have defined here units as box units, so velocity and the distance will be in box units. Pair style define the type of interaction between the particles, means how they are going to react with each other. And RC is a variable we have already defined. It defined the cutoff, and pair coefficients are defined as 1 1. Here 1 1 is in LJ unit and star star means any interaction with any other atoms. Anyone interacting with anyone is defined here as star star, means. Okay, let's move towards the run simulation section. Here comes the engine of molecular dynamics simulation. This section dictates the running of the simulation in LAMMPS. So first come the compute command. Its syntax is compute ID, group ID, style and arguments. ID is a user assigned name for the computation, while group ID is the ID of the group of atoms to perform the computation on. There is a long list of styles available with this command with its related argument used by a particular style. Specifically, the temp and partial compute defines a computation that calculates the temperature of a group of atoms after excluding one or more velocity component. A compute of this style can be used by any command that computes a temperature. Here Y flag is set to 1 only, meaning for temperature calculation only Y component velocity is included. Also, the compute of style temp computes the temperature of group of atoms, and it do not exclude any component of velocity. It calculates the temperature of whole group without excluding any components, while the temp and partial, it gives you opportunity to exclude one component or two or more. Okay, you cannot delete all components for calculating temperature. Okay, another important group of command is the fix command. It performs plain time integration to update position and velocity for atoms in the group each time step. This creates a system trajectory consistent with the microcanonical assembly (NBE), provided there are full periodic boundary conditions and no other manipulation of the system using velocity worlet integration algorithm. It simply means when particles interact, they exert forces and go to minimum of energy to minimize these forces. Fix NVE helps particles to go to the newer states by updating their position and velocity so that energy minimize overall. Its syntax is simple for present style, which is fix ID, group ID and NVE. Another important style is LAMMPS, whose syntax is fix ID. It's right here in the red. Yes, its syntax is simple. It says fix ID, group ID, LAMMPS, tstart, tstop, damp, seed, keyword and values. Tstart and tstop equals the desired temperature at the start and end of run, with damp being damping factor in time units. Seed is white noise. Like other thermostatic fixes, this fix can be used with the compute command that remove a bias from the atom velocities. This is not done by default, but only if the fix modify command is used to assign a temperature compute to this fix that includes such a bias term. Hence the purpose of fix modify command here. It tells fix number 2 to thermostat the temperature computed by thermal compute, and bias is Y component of the velocity. Basically what is happening here is that we are calculating momentum transfer in y direction. When we are thermostating, we do not want to lose contribution from y component of velocity as we need it for gradient. So we are telling thermostating to remove contribution from y direction, thermostat the whole system, and then add back the previous memory of y direction, y component of the velocity back. And what is previous memory? It is the momentum transfer. The syntax for our third fix is fix id, group id, set force, fx, fy, fc, keyword, value. And here fx, fy, fz equal force component values, and many keyword and values are possible. This command is used here to freeze atom in the wall group during simulation by zeroing their force. The enforce 2D style fix number 5, simply zero out the z dimension velocity and force on each atom in the group. This is useful for running 2D simulation to ensure that atoms do not move from their initial z coordinate. Next important command is compute chunk atom with style bin. It defines a computation that calculates an integer chunk id from 1 to n chunk for each atom in the group. Values of chunk IDs are determined by the style of chunk, which can be based on atom type or molecule ID or spatial binning or per atom property, or value calculated by another compute fix or atom style variable. Binning style here, which is the case, perform a spatial binning of atoms and assign an atom the chunk ID corresponding to the bin number it is in. N chunk is set to the number of bins. Basic syntax of this compute is compute ID, group ID, chunk atom, style, argument, keyword, and values. All the atoms are chunked into bins in y direction here. Another important command that is using this compute command is fix average chunk command with the syntax fix id, group id, average chunk, n every, n repeat, n frequency, chunk id, value 1, value 2, so on, and the keyword argument pair. Here n every means using input values every 20 time steps. And n repeat means 500 input values for calculating averages. And frequency means calculate average after every 10,000 time steps. So it after 20 steps is taking the values, chunk values, and calculating the average after 10,000 steps. And chunk id is equal to the id of compute chunk per atom command, which is named here as layers, which is compute layer after the fix 3. One more interesting style of compute command is temp ramp. Its syntax is compute id, group id, temp ramp, vdim, vlow, vhigh, dim, clow, chigh, keyword and value. This command defines a computation that calculates the temperature of a group of atoms after subtracting out a ramped velocity profile, but before computing the kinetic energy. The meaning of vdim, vlow, vhigh is velocity dimension, lower velocity bound, higher velocity bound respectively, and subtract this velocity from clow and chigh region. Clow and chigh defines the region from to subtract this velocity. Okay, this is a lot. Let's move to the final section, which is output section. This is the final section. Okay, I promise. Here the first command thermo is simple. It tells lamps to print thermodynamic information on screen after every 1000 steps. What is going to be printed is governed by thermostyle command with style custom. For present case, C title means C title, I guess it should be C tilde. Okay, yeah, it's C tilde. It means the tilt compute, which we have in the previous slide. E pair means pairwise energy, which includes van der Waals, Coulomb and long interaction energy. E total means the total energy. Press means the pressure, and pxy means xy component of pressure tensor. And run this simulation for 20,000 steps. Variable visc define the formula for calculating the viscosity. Important command here is the fix average time with syntax id, fix id, group id, average time, and every, and repeat, and frequency, value 1, value 2, so on, because we can add more values and more keyword and arguments. This command basically average global command here. The meaning of argument is the same as discussed for the fix average chunk command. Here it calculates viscosity after 1000 time steps and display the average after 1000 time steps. Another group of important command is the dump command. Dump is a snapshot of atoms. It actually dumping a snapshot of atoms quantities to one or more files after every n time steps in one of the several style. For example, it can be images or it can be a video. It depends. Okay, so far what we have done, we have been through a lot of syntax, and it's okay not to memorize all these stuff for any good reason. You can always refer to the LAMMPS manual for any query you have for your problem. Only important thing is to think of your problem in hands in terms of LAMMPS setup. Okay, let's summarize the problem we have discussed yet with lots of syntax structure. For calculating the viscosity of fluid, we are using LAMMPS, which is empty code. It requires fluid and some solid thing, which is wall here, to slide on. After applying shearing, we transfer momentum in y direction, and so does the other layer. Using the LAMMPS, we calculate the temperature. Just a minute. Using LAMMPS, we calculate the temperature due to y component velocity. We are also calculating temperature of whole group of moving fluid. We are thermostating the temperature governed by the y component of velocity, removing the bias, and also updating the position and velocity of the whole system. By binning the system, we are able to study the effect of shearing on each layer individually. And we are dumping the snapshots so that we can visualize it later with other softwares. Okay, so far so good. Let's end the tutorial here. Let's end our discussion here, and in the next video we will write this code step by step in Notepad, and we will see that how things are working. And the purpose of this tutorial was to expose to the syntax of the LAMMPS command. In the next video we will formulate our problem, which is viscosity here, in detail. So hope to see you guys in the next video.